Finishing up this section, we're going to look at colligative properties and molar mass determination. So earlier in this book, actually in Gen Chem 1, you learned how to calculate a molecular formula from an empirical formula when given the molar mass. But how do you know the molar mass of an unknown compound? An experiment must be carried out to find this crucial piece of information, and one way to do so is to use a colligative property of a solution of the compound. So we can look at the change in vapor pressure, boiling point, elevation, freezing point depression, or osmotic pressure to find the solution concentration. If we know solution concentration, we can figure out how many moles of solute there are and then find the molar mass. Let's look at how to find the molar mass from boiling point elevation. If we have a solution prepared from 1.25 grams of oil of wintergreen and 99 grams of benzene, and it has a boiling point of 80.31. Let's determine the molar mass. First, I'm going to look up the boiling point for benzene. Its actual boiling point, and this is a table in your text, is 80.1. So let's look at that change, or the boiling point elevation. It told us 80.31, so I'm going to do 80.31 minus 80.1. That delta T boiling point is 0.21 degrees Celsius. Let's recall back to our boiling point elevation equation. The change in boiling point elevation is equal to the boiling point constant times the concentration of the solute. So I'm going to put in that 0.21 on the left, look up the boiling point constant for benzene, and times that by our unknown C. We can find this concentration. Divide both sides by 2.53, and we found the concentration of the solute of 0.0830 molality. So we used the boiling point elevation to calculate concentration. The next thing we're going to do, we're going to find the amount of solute in the solution from the concentration. We know that we have 99 grams of benzene. Remember, molality is moles per kilogram. So I need to change that grams into kilograms to get rid of that denominator, telling me that I have this many moles of solute. It told me that I had 1.25 grams of this wintergreen. All we have to do to find our molar mass is we take grams divided by moles to give me my grams per mole. So it's about 150 grams per mole. And it actually has a formula of C8H8O3 and a molar mass of 152. So we were pretty darn close. And considering that we were working with only two significant figures, we're acceptably close to the actual value. Here is one using freezing point depression. We have an aluminum containing compound with an empirical formula of this. Find the molecular formula if we know how many grams of a compound dissolves in 23.46 grams of benzene and a freezing point of 5.265 degrees Celsius. Again, let's find that freezing point depression. I looked up benzene's freezing point, and we're going to subtract our freezing point given and its actual freezing point. So we have a freezing point depression of negative 0.235 degrees. And I looked up the freezing point constant, and we're going to divide both sides by that constant to get our molality. We found the molality. We need to get rid of that kilograms of benzene. So I'm going to times it by 0.02346 kilograms, changing those grams into kilograms. That gave me moles of my solute. And again, I'm going to take my grams of solute divided by moles of solute to figure out my molar mass. Recall back to Gen Chem 1, if I know my molar mass and I know my empirical mass and I divide the two, I will get really close to a whole number, and I would multiply everything in my empirical formula by that number. So I'm taking my molar mass, and I found my empirical mass, which was about 104.1, and I get a whole number of 4, so I need to multiply everything in my empirical formula by 4. That would give me my molecular formula. Let's look at a problem using osmotic pressure and molar mass. Beta-carotene is the most important of the A vitamins. Calculate the molar mass of beta-carotene of 10 milliliters of a solution in chloroform containing 7.68 milligrams of beta-carotene, has an osmotic pressure of 26.57 millimeters of mercury at 25 degrees Celsius. Well, let's find the concentration. Since I know osmotic pressure, I know R, and I know temperature. So I'm going to rearrange my formula here to solve for concentration. I was given millimeters of mercury. Remember, I need to convert to atmospheres because my R constant is in atmospheres. So I would have my osmotic pressure on top divided by R and T. Make sure you convert that into Kelvin. I got a concentration of this. I can then calculate the amount dissolved in 10 milliliters of solvent. It told me it was 10 milliliters, which is 0.01 liters. That will get rid of my liters, leaving me with moles. And it also told me I had 7.68 milligrams. Well, I need that to be in grams, so I can do my grams per mole. So 7.68 milligrams is 7.68 times 10 to the negative 3. Or you could have written 0.00768 grams. And I would get a molar mass of 538 grams per mole. And if you actually looked it up, beta-carotene is a hydrocarbon with the formula of C40H56, and its molar mass is 536.8. So again, very close. Let's do one more practice problem using osmotic pressure. We have a 1.40 gram sample of polyethylene, a common plastic, dissolved in enough organic solvent to give 100 milliliters of solution. What is the average molar mass of the polymer if the measured osmotic pressure of the solution is 1.86 millimeters of mercury at 25 degrees Celsius? We want to find our concentration again since we know osmotic pressure and R and T. Convert to atmospheres, convert to Kelvin. So I got my concentration. Taking my concentration, I'm going to times it by volume to get rid of my liters. 100 milliliters is 0.1 liters. That gave me moles of my polyethylene. And I was told that I had 1.4 grams, so I'm going to do 1.4 grams divided by moles to get grams per mole. And assuming that this polyethylene is composed of CH2 units, 1 carbon and 2 H's has a molar mass of about 14 grams per mole. So if I took this molar mass and divided it by a CH2 unit, that would be about 10,000 units long for that polymer. We're next looking at the colligative properties of solutions containing ions. In the northern United States and Canada, it is common practice to scatter salt on snowy or icy roads or sidewalks in the winter, like it is here where I live in Michigan. When the sun shines on the snow or patch of ice, a small amount melts and some salt dissolves in the water. As a result of the dissolved solute, the freezing point of the solution is lower than 0 degrees Celsius. The solution eats its way through the ice, breaking it up, and the icy patch is no longer dangerous for drivers or walkers. Salt, or sodium chloride, NaCl, is the most common substance used on roads because it's inexpensive and it dissolves readily in water. Its relatively low molar mass means that the effect per gram is large. In addition, salt is especially effective because it's an electrolyte. That is, it dissolves to give ions in solution. We start with our solid salt, and it dissolves into Na plus ions and Cl minus ions. Recall that colligative properties depend not what is dissolved, but on the number of particles of solute per solvent particle. When 1 mole of sodium chloride dissolves, 2 moles of ions form, which means that the effect on the freezing point of water should be twice as large as the expected for a mole of sugar. If I had 0.1 molal solution of sodium chloride, that really contains 2 solutes, 0.1 molal of Na plus ions and 0.1 molal of Cl minus ions. What we should use to estimate the freezing point depression is the total molality of solute particles. So this shows us our total molality. We're going to take the molality of the Na plus ions plus the molality of the Cl minus ions. So 0.1 plus 0.1 is equal to 0.2 moles per kilogram. Then I can find that freezing point depression by taking the freezing point of water times it by 0.2 to get that it would freeze 0.372 degrees lower than the freezing point of water. So to estimate the freezing point depression for an ionic compound, first find the molality of the solute from the mass and molar mass of the compound and the mass of the solvent. Then we multiply the molality by the number of ions in the formula. That would be 2 for NaCl because there's 1, 2. 3 for Na2SO4 because there'd be 2 NAs and 1 SO4. 4 for LaCl3. There's 1 La plus 3 chlorines. And 5 for aluminum sulfate. 2 aluminums plus 3 sulfates. Hopefully you get the idea. As the concentration of NaCl decreases, the freezing point depression for NaCl approaches but does not quite reach a value that is 2 times larger than the value determined, assuming no dissociation. Likewise, the freezing point depression for sodium sulfate approaches but does not reach a value that is 3 times larger. This is called the Van Hoff factor, after Jacobus Van Hoff, who studied this phenomenon. The Van Hoff factor is represented by the variable I. We can then write for solutions of electrolytes that this, and here we have the boiling point elevation, but it could be freezing point depression. The constant for the boiling point times the molality of the solute times I. Now, I, like we just said, NaCl would be 2 because there's 2 ions. Or the aluminum sulfate would be 5 because there's 2 aluminums and 3 sulfates. But it would be 1 for non-electrolytes because they're not dissolving into ions. This Van Hoff factor can be used in calculations for any colligative property. Vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure are all larger for electrolytes than for non-electrolytes of the same molality. So if we were to look at 1 mole of sucrose, sucrose is a molecular compound, so that would be 1 mole of particles of solution. Again, NaCl is an ionic compound, 2 moles of particles. Calcium chloride would be 3 moles of particles, 1 calcium and 2 chlorines. Let's look at this sample problem. We have a 0.02 molality aqueous solution of an ionic compound, and it freezes at negative 0.0640 degrees Celsius. How many ions does each formula unit of that compound produce on being dissolved in water? Well, first we're going to calculate the freezing point depression for the solution, assuming the salt does not dissociate into ions. So we'll use our freezing point depression is equal to the constant times the molality. We were told that molality is 0.02. We look up our constant freezing point constant for water because it tells me it's in water. And I find that our freezing point depression that's calculated is negative 0.0372. Now let's compare those delta T, the freezing point depressions. We're going to take our measured that we were given divided by our calculated. We are given negative 0.0640. That's our numerator. We calculated the denominator, and I got 1.72. So the I, the Van Hoff factor, is much greater than 1. It's closer to 2. We're going to round it to 2 and say that there's 2 ions in solution. For this guy, we're going to find the freezing point of 525 grams of water that contained 25 grams of sodium chloride. Assume I, the Van Hoff factor, is 1.85 for sodium chloride. So let's find the concentration here. I went from grams of NaCl to moles of NaCl. So I got 0.42779 moles. I'm going to divide it by my kilograms of water to get 0.8148 molality. And then I'm going to plug it into my freezing point depression. Take my water constant times the molality times my Van Hoff factor I was given, the 1.85. And I got a freezing point depression of negative 2.80. And water freezes at 0, so 0 minus our freezing point depression, the freezing point would be at negative 2.80 degrees Celsius. And that wraps up section 4.